This is going to mark the beginning of the second half of Chapter 8. Chapter 8 is just titled the Applications of Trigonometry. So it's not exhaustive in the set of all applications of trigonometry. Trigonometric applications range way too much for that to be contained in a single chapter. So these are just immediate applications of trigonometry. Honestly, I think it's because I don't know if they did the best job gathering all of the trigonometric topics and organizing them in a specific way. I'm guessing they just couldn't see where all these extra topics fit, and they just stuck them in a chapter after the first three. Chapters 5, 6, and 7 were the major ones over the trigonometric stuff. There's just an 8th chapter, or this is a 4th chapter for the trigonometric stuff. So it's a bunch of stuff, and it's kind of all over the place. And then in the last two sections, 8, 7, and 8, 8, those are even different concepts altogether. One of them is slightly trigonometric, the other one not even trigonometric that much. So 8.5, this one, together with 8.6, will serve as the vector treatment of the complex plane. So this is really an application of vectors. We're going to think of complex numbers as vectors, which this is a direct extension of two-dimensional vectors like the ones we were seeing in 8.4. So if you understood the stuff from 8.4 very well, this is going to be pretty simple. This is kind of cool mathematics too. One of my favorite courses, because I was a math major when I was in college, when I was doing my bachelor's degree, this was one of my favorite courses that I had taken, period. This I took as an elective course, and it was called Complex Analysis. So basically, you take your first 3 semesters worth of calculus as like basics. Those are your math basics, the first 3 calculus courses. And there's a couple of others too that are basic. Then you take your actual core courses, and there's also electives that you're allowed to take too within the department. This is one of the courses I took as an elective course. It was a lot of fun too. This is just calculus, but on the complex plane. So it was an extra calculus course, but it was calculus with complex numbers. So the stuff that we're going to see here is maybe the first couple of sections in the first chapter of the book that I was looking at. So it doesn't go too crazy, but it's still a lot of fun. The geometry on complex numbers is much more fun to work with and much more intuitive than working on a number line. Working on a number line sucks, in my opinion. On the complex plane, there's a bunch of neat little geometrical tricks that make things a lot easier, more convenient, and it makes it a bit more intuitive too. It's a lot easier to think of functions on a complex plane sometimes than it is to think of them on a number line. Number line is a little tougher. But anyway, so we're going to go into 8.5, and we're looking at a polar treatment. So they're introducing the term polar, and it's because the section that follows these two, 8.7, so it's 8.5 and 8.6 together, which they're just a continuation of each other. That should have just been one section, really, but it would have been a long section. The section that follows these next two is the stuff on polar coordinates, polar equations, polar graphs. So trigonometric, polar, they almost mean the same thing, and we're going to get to that in just a little bit. So it's just another term or another name for trigonometric. So we'll get into it. The complex plane, and I don't like their stuff. I probably should have taken the time to type that out. Sometimes I type stuff out, sometimes I don't because of time, and lately, because of the current situation, I do have a lot of time on my hands. Most of it's actually for recording and editing and uploading stuff, but this is probably one I should have redone, because I find myself moving over to the side a lot and having to explain things in my own terms, and it's probably nicer if I had that stuff already printed out. So the idea is we study real numbers. So very early in y'all's mathematical or academic career, we start thinking of numbers along a line, along a ruler maybe, and the ruler extends forever on both sides. And we can talk about a reference point, which we normally use 0 as that reference, so we're going to call it the middle. No such thing as a middle, though, if we're talking about an infinite line. So there is some place we call it 0. And we could think of whole number tick marks. Let's say 1's here, 2's here, 3's here, and then we can go to the backwards negative numbers, -2, -3, and so on. It keeps on going. So you can keep track of numbers. And basically any real number, a number we call it real, if there's some sort of assignment on, or some sort of assigned location on that line that represents that number. So a number we say is real if we can find it somewhere on that line. So if there's a point on that line referenced to 0, where that point can live on and represent that number, then that number we consider it real. So there's different types of real numbers. So here I've drawn a few of them, and those are only integers. So integers are whole numbers. Whole numbers keep on going, starting at 1, keep on going that way. If we include 0, we call those the natural numbers, and there's kind of a debate. What exactly is a natural number? What does it include 0? Does it not include 0? Stuff like that. Most textbooks, and I was on the side where no, you don't include 0 for the longest time, and I've recently accepted using 0 as a natural number. So 0 is a natural number. Now, the negatives of the natural numbers together with the natural numbers makes the set of all integers. So integers, that's a fancy term, but an integer really is just all natural numbers, 0 and all the counting numbers, plus the negatives of the counting numbers. So those are integers. So then what are fractions? If I take fractions so that way the numerator denominators are integers, then you get what are called rational numbers. Rational numbers make up an infinite amount of numbers in between and on those tick marks. So you could think of dividing 3 by 2, and if I divide 3 by 2, you get this number here at 1.5. You could think of dividing 2 by, let's say, -3. So if I take 2 and divide that by -3, you get negative 0.666666 something something, keeps on going forever, and that's somewhere around here. So this is -2 divided by 3, or 2 divided by -3 in that case. So if I take any two of those tick mark values and divide them, I'm going to get a number on this number line, unless of course the number I choose in the bottom to be 0. So I can't divide by 0 obviously, but if I take any other combination of integer values, you're going to land somewhere on that line. And it looks like it's going to fill up the entire line. Truth is, it doesn't. There are numbers in between these that those rational numbers don't contain. So the number line contains another infinitely large set of numbers that are not real numbers. That are not rational numbers, sorry. We call them irrational numbers. Now, it's a mathematical fact, it turns out, that there are more irrational numbers than there are rational numbers. Both sets are infinitely large, but one of them is larger than the other. And that's a weird one to play around with in your head. How can two infinitely large sets have a different size? So they're both infinitely large. Aren't they the same size? So no, it turns out that there are different types of infinities, different levels of infinity, and there are some infinites that are larger than other infinite values. So it turns out that the set of all irrational numbers is what we call uncountably infinite, whereas the set of all rational numbers is called countably infinite, also known as denumerable. So it's a bunch of mathematical jargon, but there's all these different types of numbers that fit on the number line. So point is, when we were dealing with square roots as mathematicians, solving quadratic equations, cubic equations, quartic equations, quintic equations, and so on, polynomial equations of general types, and we've gone through this tons of times, sometimes the solutions are non-real. So if I have maybe like an equation that looks like this, x cubed minus 1 equals to 0, there is definitely a real solution to that, and I would say x equals to 1 is one of the solutions, right? But we learned earlier, with a power of 3, we can expect at most 2 more solutions. And this one actually has 2 more solutions. However, those 2 solutions are not real numbers. So there's only one real solution, it's x equals to 1. But there are 2 complex solutions besides x equals to 1 that satisfy that equation as well. We're going to see later on that these types of equations, even if they only have one real solution, will have more distinct solutions that are non-real. And we've seen that before with the quadratic equation. So sometimes quadratic equations have no real solution, but can have 2 complex solutions, 2 non-real complex solutions. So what we do is we invent these types of numbers, or a new numerical system to describe these new numbers, which we can consider 2-dimensional numbers. I'd like to erase those dots, but I don't know if I can. So let's say, for example, this number makes total sense. Let's say 2 plus 3i. So 2 plus 3i. I know how to graph real numbers. Is there a way that I can graph complex numbers? And the answer is yes, we can. So I have 0 here. Let me make a y-axis out this way. So Instead of calling that x, I'm going to call that z, and there's a reason for it. 2 is the real part. Real numbers we're going to take to be an x value. 3i altogether is an imaginary number, and we're going to take imaginary numbers to be drawn on the second axis. Since imaginary numbers are multiples of I, and the multiple that it is of I can take on any real value, positive, negative, irrational, rational alike. So we're going to make another real axis, or another number line that represents a real number multiple of the number I. So we'll have x here, and we'll have y here. And if I want to graph 2 plus 3i, then I need to mark these. So it's 1, 2, let's say 3 again. So I'm going from negative 3 to 3, negative 1 here, negative 2, negative 3, let's say. So because of where I had the 0, it's kind of weird. But either way, and I kind of circled these. I kind of want to erase them. I don't know if it's possible to without erasing the whole x-axis. Doesn't look like it. Yeah, and I had to erase the whole x-axis. So let's see if I just draw that all over again. And that's not too bad. I'm going to work with that. So if I wanted to graph 2 plus 3i, your real part is 2. Your imaginary part is 3. We take those as x and y coordinates, and there we go. That's the system for graphing complex numbers. So this is the complex number 2 plus 3i. Instead of thinking of it as a complex number, we could think of them as ordered pairs, 2, 3. So really, complex numbers are just ordered pairs. There's a real part, and then there's an imaginary part. We just don't take the I into account. The I is there just to tell us which of the two it is, an x value or a y value. So 2 plus 3i is the same thing as 2, 3. So y is equal to some number b times I, and x is just equal to a, where z is the complex number a plus bi. So we could take any complex number, a plus bi, and graph it this way. A is going to get graphed on the x. B by itself is going to get graphed on the y without the I. So the I is just a place marker. The I means that's the second coordinate. That's all that means. Okay, so there's several other things. So a real number, a plus bi, can also be treated as a ordered pair, a comma b. And because it can be treated as an ordered pair, then there's a one-to-one correspondence to vectors in the two-dimensional coordinate grid. So that means complex numbers, I'm going to write it out this way. Complex numbers are vectors. There's a lot more to it to prove that they're vectors. There are rules that mathematicians have to verify vector spaces. So the complex plane is a vector space. So there's a set of 11 rules. I think it's 11. If not, it's 9. I think it's 11 rules total. And if your little mathematical space satisfies those rules, then it's a vector space officially. And it satisfies all those rules as long as I properly define addition and properly define, what was it, scalar multiplication. You remember those were the two operations that we define in a vector space. So there was vector addition, and then there was scalar multiplication. And here's the way we do it. So we have to define addition and scalar multiplication. So z1 is equal to a1 plus b1, let's say. z2 is another complex number. We'll say that's a2 plus b2 times I. How do we define? So I'm going to put DEF for definition. z1 plus z2 is equal to, we'll just combine the real number parts, so a1 plus a2, plus we're going to combine the imaginary parts, b1 plus b2, and then times the I. So if we want to add two complex numbers together, you combine like terms, the reals together and the imaginaries together. So there's our definition for vector addition. What about scalar multiplication into a single complex number? So let's say my scalar is, I already used a and b, so I guess I'll use c. c times z1 is equal to c times a1 plus b1i. You could distribute the c, and it's c times a1 plus c times b1. I'm drawing an I, b1, I. So that's how we define. So if you wanted to write it as an ordered pair, then this would be CA1, comma CB1, and then close parentheses. So that's how we define scalar multiplication and vector addition. So if I wanted to write this one as an ordered pair, it's A1 plus A2, comma B1 plus B2. And if I define vector addition and scalar multiplication that way, then rest assured that's going to end up becoming a vector space. This is a space of vectors then. So then the complex plane is also a vector space. So then I could think of these as vectors. If that's the case, then I could draw arrows from the origin, which the origin now, that's interesting. What does the origin represent? Any point on this plane is a number. So let's talk about points on this grid. Let's take the origin on its own. What are the coordinates of the origin? The coordinates of the origin are 0, 0. How do I write that as a complex number? 0 plus 0 times I. Remember, it's the real part plus the imaginary part times I. So what is 0 plus 0 times I? 0 times I is 0, plus 0 is 0. So then the origin is the real number 0. Now here's the thing. 0 is the only real number that is also an imaginary number. It's on the imaginary axis. Any number on the imaginary axis is an imaginary number. So that kind of seems a little contradictory. How can something be real and imaginary at the same time? Well, depending on how you define things, and if that's the way if we define things, 0 happens to be both, and it's the only number that is both a real number and an imaginary number at the same time. So 0 is not a non-real imaginary, it's a real imaginary. That's kind of interesting. So if I take another random point, let's say here, -1, 1. So -1, 1 is the imaginary or the complex number, -1 plus I is how we write that. So what about numbers that are on the x-axis? Let's say this number over here. That's literally just -3 plus 0i, which is just -3. Numbers that are on the x-axis are purely real numbers, non-imaginary. So they're purely real. Let's flip that. Let's say I take a number on the y-axis only. So if it's on the y-axis, the x-coordinate is 0, the y-coordinate is -2, so that's 0 minus 2i, which boils down to -2i. Purely imaginary, no real part. So the real part is 0. So that's a purely imaginary number. So those are the basics behind the geometry of complex numbers. So that's the realm that we work on. That's the playground that you get to play with. So several other things, which I'm going to probably move this down a little bit. Another set of things that we want to know before we move on. So if I go back to a complex plane, blank canvas. So let's say this is A, this is B, and the vector A comma B is the number Z, A plus BI. Or you could write that as an ordered pair. You're not wrong if you write this as an ordered pair instead, A comma B. You can do it both ways, one of both ways. It doesn't really matter. So, several things. Because it's a vector, it has a directional angle, and it has a magnitude. I forgot the name of the person that proved that this was a vector space. There was a particular person. There's a bunch of stuff named after him in this realm, and we'll probably see his name later. The next section is called de Moivre's theorem, and it's not that person. It's somebody else. It's with an A. I forget the name of that guy. I don't even remember. But instead of calling them a magnitude and a directional angle like we normally do in vector algebra, he called them something else. So if we take the magnitude, which I'm going to write the word magnitude so we know what it's talking about, the magnitude of Z, which we denoted it as the absolute value of Z. This in complex analysis is called the modulus. That's the fancy term for the magnitude of a complex number. Literally, it's just the magnitude of the vector Z. But the fancy term in complex analysis is called modulus. The angle of Z, which a lot of the times we just call it the angle of Z. A lot of the times that's the symbol for it. which we just call it theta. The name for that is the argument. And we've used that term before for trigonometric functions. It's the number you plug into a function, therefore we call it the argument. So modulus and argument, those are the fancy words for just magnitude and direction of a vector. So in complex geometry, they're called modulus and argument. So we'll see those every now and then. What are the formulas for those? The formulas are almost identical to the one, actually they are identical to the ones that we saw in 8.4. So the modulus of z is equal to the square root a squared plus b squared. What about the argument? The angle of z. This is, well, first off, tangent. This is the formal way to do that. So tangent of the argument is equal to y over x. In this case, it's b over a. Those are my formulas. So tangent of the angle is equal to b over a. Those are our two vector equations that we're going to work with in this particular section. So those are all of the basics. Also, there's a bit of a symbol. If I take all of these points together as a big set, one thing I'm leaving out, there's a name for it. The entire plane, the complex plane. So the entire playground of points that we get to play with, we call, or the symbol that we use for it, like the set of real numbers, it's a C but with a stem on it. So this is also the same thing basically as R2. It's the two-dimensional real coordinate grid basically. But we're understanding one of those to correspond to imaginary numbers instead, so we call it C. So there's a symbol for it. Okay, so we'll move on. We're going to look at example 1. Find the sum of these two particular complex numbers. And they gave us a graph here that I get to work with. So nice. But either way, find the sum of 2 plus 3i and negative 4 plus 2i. Graph both complex numbers and their resultant. So what I'm going to do first is show you the algebraic way to do this, which you're already well aware of. We've done this before chapter 1. This was the very, very first section we looked at in chapter 1. It's not the first section in chapter 1, it's the first one that we looked at, 1.3. So either way, you're adding 2 plus 3i with negative 4 plus 2i. We think of these as polynomials. You think of I as a variable, and you combine like terms. So 2 minus 4 plus 3i plus 2i. That's going to be negative 2 plus 5i. So that's the algebraic way to do this without graphing. So we already knew that. So most of you should have been able to figure that out on your own. Just combine like terms. So when you're adding and subtracting real complex numbers, you're combining like terms. So why the graph? So the graph is there because we're treating this as a vector space. So let me graph both of those. 2 plus 3i is graphed here. That's this vector. The other vector is negative 4 plus 2i. So negative 4 plus 2i is over here, and that's this vector. We're trying to add those two. Now if you remember, adding vectors is supposed to play this way. So adding vectors is supposed to satisfy the parallelogram rule. So the parallelogram rule means if you take one of those vectors and then you add the other vector starting at the end of the first one. So if I take negative 4 plus 2i and then where that's at here at negative 4 plus 2i at the end, so negative 4 comma 2, then I move according to the other one. The other one is 2 plus 3i. So 2 means 2 to the right and then 3 up. So 1, 2, 3 should leave me here. So you could verify that visually really quick. And from that point at negative 4 comma 2, you move to the right 2 and then you move up 3. Or I could have done it the other way around if I draw this in red instead. So if I had started at 2 plus 3i, and if I move 4 to the left and 2 up, I'll end up here. I could draw that from here, if it lets me, this way. And that's supposed to make a parallelogram. And the resultant is the diagonal starting from the origin where you started off, all the way to the terminal point. And that's supposed to be from here, this way. Now, you double check. If you did the parallelogram right, then the point that you ended up at should have the same coordinates as the one we boxed over here, -2, 5. And yeah, if you check it, -2, 5 is how that works. So the key to adding two complex vectors, combine like terms. You have to combine like terms. And it's going to play the same as vector addition. So that's just example 1. That's a pretty simple one. There might be some homework problems like that. So all they wanted was the graph and the resultant. So we wanted to graph both vectors and the resultant. So I added some extra stuff I wasn't supposed to add. So just the vectors themselves plus the resultant. And there we go. So I drew the whole parallelogram. I wasn't supposed to draw the whole parallelogram. Okay, so the polar form of complex numbers. So we are going to call back to memory the polar equations. Polar equations are trigonometric facts that can change our x, y space, a rectangular space, to a distance and angle space. So we have a r, which is a radius, a distance, and an angle. So if I know two rectangular coordinates, x and y, one horizontal, one vertical, we can translate that to a vector space, angle, and direction. And we call this a polar transformation. So x and y, if those are perpendicular to each other, those are straight lines that are perpendicular to each other, and that's how we measure coordinates. We call that rectangular. This one we call polar. If the system relies on an angle and a distance, that's called polar. So that's introducing the new coordinate system that we're going to see in 8.7, and we're going to be changing back and forth between rectangular and polar, which we see that a lot in physics, we see that a lot in engineering. The equations look uglier, but the manipulations mathematically become a little easier for working with distances and angles versus x coordinate, y coordinate, z coordinate. It's better to talk about angles and distances for the most part if we're talking about physics and engineering. So this is the way that we start that in an elementary sense, 2 dimensions. So you might recognize this equation. X is equal to r cosine theta. You're probably saying, nah, I don't recognize that at all. Divide by r both sides, and you get x divided by r is equal to cosine theta. That's our initial definition of cosine that we went with at the beginning of January. Same thing with this one. Y is equal to r sine theta, divide by r both sides. Y over r is equal to sine. You all remember those, I hope. And then what's this? This is another one that we remember. R is equal to square root of x squared plus y squared. That's not how we learned it earlier. The way we learned it, actually no, that is the way we learned it earlier. The other way, r squared is equal to x squared plus y squared, which is literally the Pythagorean theorem. And then of course we remember this one. Tangent theta is equal to y over x. So that's just the third definition. Those 3 definitions are needed for building a trigonometric space. So those are just trigonometric facts, basically. So those are the facts that we use to move back and forth between rectangular coordinates and polar coordinates, which polar is the new trigonometric. So trigonometric has way too many syllables. I'm using the word polar, plus I also sound smart when I say the word polar. So we're changing that to polar now. And there's a specific reason why. It's because now we're changing coordinate systems. So polar is the name of the system. Okay, so now I'm going to try to guess, like what the hell are they saying in here? So I'll try to figure that out. The something something or something something of the complex number x plus yi is, okay, so this is the trigonometric form or polar form of the complex number x plus yi. So a different way to represent a complex number is equal to r times cosine theta plus I sine theta. And there's a proof for that. X is equal to r cosine theta, y is equal to r sine theta, z is equal to x plus iy, or yi. I normally write the I at the end. So y times I. Now earlier we were saying it was a plus bi. Same thing, x and y, a and b. A and b are x and y coordinates, so same idea. Well, what's x? X is r cosine theta, y is r sine theta, times I. Notice how they both have an r inside? So this one has an r, this one has an r, factored out. R, parentheses, cosine theta, plus sine theta times I. Now they're writing the I first because you don't want to confuse it with, is it inside the argument? Is it part of theta? Is it what? So it's I, and then on the outside times sine of theta, and then close parentheses. That is the polar or trigonometric form of how to write a complex number. Okay, so let's see. The expression cosine theta plus I sine theta is sometimes abbreviated CIS of theta. Using this notation, R times cosine theta plus I sine theta, let's see, this is written as R CIS. So it's called a CIS function of the cosine I sine function. But either way, that's the way that you write it. So they might have, no, they didn't hint at it, like what's it called? Okay, so example 2, converting from trigonometric form to rectangular form. Oh, and we're going to have to remember our unit circle. Some of you are really good students and probably still have your notebook. And to those of you, I salute you like 100%. If you still have your notes and you're still doing this like 100% with me, all respect to you. And if you have your unit circle, that's great. So 135 is it one of those values in the unit circle? That's bad that I forgot. So yeah, it is. 135 is in the second quadrant with a 45-degree reference angle. So the distance this way is 45 degrees. Distance this way is 135. Okay, so write 10 cosine 135 plus I sine 135 in rectangular form. So what this ends up feeling like is all you're doing is unit circle math. So it's going to end up feeling that way. So I'm going to call that Z. So that way Z is equal to 10, then we'll figure it out. Cosine 135 plus I times sine, same angle, 135. So that is actually, if you want to think of it this way, before I even write it out, let me see what this means. Cosine 35 degrees plus I sine 35 degrees. X coordinate is cosine of 35. Y coordinate is sine of 35. So in other words, we're talking about on the unit circle, X coordinates here, Y coordinates there. We're talking about a point on the unit circle. If it wasn't for the 10 on the outside, what does that 10 do? What the 10 does is it changes the radius of that circle from 1 to 10. And I can't draw one that's 10 large. Right, so I'll just pretend that that's 10 all the way around. We're talking about this point here. If that's the radius equals to 10 circle, this right here is the radius equals to 1 circle. We're talking about this point out here. This is the Z value that we're talking about. So really what we're trying to do is we're trying to find the X and Y coordinates of that point out here. But instead of thinking of it rectangularly, we're thinking of it polar, in a polar way. So really that's something that could be drawn on a XY coordinate grid. Radius is 10. So if you think of the unit circle, if I were to, I'm going to erase all this. So I'm going to try to zoom in as much as I can to see if I can drive this point home. Unit circle on this coordinate grid is a tiny little thing here. This is the unit circle. So we're zoomed out quite a bit. So that is the unit circle. So sine and cosine live in here, and it oscillates back and forth over that circle. So that's the unit circle. What circle am I really working with right now if I'm talking about a radius of 10? We're talking about this circle. So it's a radius of 10. And I'm not going to try to draw the rest of that because it's going to look ugly. That arc already looks kind of ugly. So we're talking about 45-degree angle here. We're talking about this point. What point is that? That's the question. So this right here is an argument of 10 and an angle, a radius of 10. So that's a modulus of 10 and an angle of 135 degrees. So 135 degrees looks like this. So we're trying to get you to think outside of the rectangular box. This is 135 degrees. And that's a radius r equals to 10. So we could think of them as x and y coordinates. There's a point here and another point here. So we don't know exactly where it's at. So if I had drawn that circle perfectly, that should have been the same x and y coordinate. They're kind of way off. So 45 degree, we know that that's straight down the middle. So we're talking about that point specifically. So we'll see what that is. And I have a calculator ready so if we can estimate them to the best of our ability. So we're talking about 10 times cosine. So To put that into practice, this is the same thing as 10 CIS of 135. It's going to get very annoying to write cosine of the angle plus I times sine of the angle. That's the reason why mathematicians came up with this little abbreviation, CIS, and it turns out there's an even simpler abbreviation past the CIS, which I don't know if we'll have time to see that, but it'll probably be at the end of the year, last few weeks, which if I have time, then I'm going to go over it. Maybe, maybe not. I know with my dual class, I will be going over some of that because there's going to be the stuff that STC is going to have me go over. Our STC course ends the 15th of May. So STC dual enrollment, last day of classes is May 15th, and or May 14th, sorry, and you're officially done with the semester for STC. There are still 2 more weeks left with no final exams, from what I understand. There's going to be no memorial final exams. Now, don't quote me on that because I'm not well versed in the grading guidelines. So I should be well versed in the grading guidelines because I've been through a ton of trainings over the grading guidelines and I seem to have forgotten. But from what I remember, I don't think we're going to have final exams the way that we're used to having final exams. Those last 2 weeks are going to be for regular instruction from what I understand. So if that's the case, I'm teaching calculus those last 2 weeks in my dual enrollment class for sure. So you'll see some calculus stuff. And there's going to be a little bit on some of this here that we're going to see. So I'll concentrate on some stuff to extend the trigonometry, not just to go into calculus for the sake of going into calculus, but extend it to the trigonometric concepts that you're going to be needing to extend them anyway because it's going to suck in calculus later on. So you want to take advantage of that. So we'll keep on going. So 10 cosine I sine of 135 degrees. So what does that end up equaling to? So what is cosine and sine of 135? So it's 10, and I'm going to think of this as 2 coordinates. Cosine 135, comma, sine of 135. If you remember your unit circle, those are on your unit circle at 135 degrees, or 3 pi over 4, negative square root of 2 over 2, comma, square root of 2 over 2. And if you already had your unit circle and you were waiting for that and you already knew that, sorry, it took a long time, you multiply that by 10. So you distribute the 10 in there. Remember multiplication by a scalar? You just distribute the 10 into both of those. 10 and the 2 on the bottom, they reduce to a 5. So that's going to be negative 5 square root of 2, comma, 5 square root of 2. Or if I write that in rectangular form, negative 5 square root of 2 plus 5 square root of 2. And I'm going to write the I at the very end, which you could. Or, and this is kind of weird because there's going to be an inconsistency with how you write these. You can write the I at the beginning, which they tend to do, and that's going to look weird writing the I before the 5 and the square root of 2. You can write the I at the very, very end as long as you're not confused as to where the I is at, outside or inside the square root. It's definitely outside the square root. But writing it in the front like this is kind of weird, and I'm very inconsistent with the way that I write them. If there's mixtures of whole numbers and square roots, I write the whole number first, then the I, then the square root. And we've seen it that way, written that way, when we covered complex solutions to quadratics using either completing the square or factoring, not factoring, sorry, a quadratic formula. That's the way I'm used to writing it anyway. So here's our answer for the rectangular form of that particular number. So that one took a while, but you want to make sure you understand that. Okay, converting between rectangular and trigonometric. So you can sketch a graph of that number on the complex plane like I did over here. I tried explaining what that would look like on the complex plane, and over here as well, what that would look like on the complex plane. So same idea. You can start with a graph. That's usually your best bet. Start with a graph. Second, you can find r using the equation x squared plus y squared square root is equal to r. I should have written r first. So use the equation r is equal to all of that. Oops. Meant to move it. And it's not letting me do it. There we go. R equals all of this. You can find theta using the equation tangent theta is equal to, in this case, y over x, where x is not equal to 0. Then you would take an inverse tangent and then figure out what quadrant it's in, and then add 180, subtract from 360, subtract from 180, stuff like that, to figure out what that's going to look like. So that's how you would switch between, back and forth. So this is probably going from rectangular to trigonometric or polar. And if you wanted to go backwards, the other way around, from trigonometric to rectangular like we did here, then you just cut straight to z is equal to r times cosine theta plus I sine theta. That's the way we did it in this particular problem. But if you wanted to go the other way around, you would use those equations. So I'm guessing the next one's like that. Yeah, write each complex number in trigonometric form. So we're going to talk about the first one, letter A, 8 minus 8i. And like they said, graph it first. Where is 8 minus 8i? What quadrant? I think that's the fourth quadrant, no? Positive 8 as an x-coordinate, negative 8 as a y-coordinate. So say that's 8, and this is 8. So negative 8 here, positive 8 here. We're talking about this number, or this vector. Either or. So we want the trigonometric form or the polar form. So the trigonometric form requires an angle and a radius. So how do I find the angle theta? So some of you already know what it is just by looking at it. If they're the same x and y coordinate absolute value, 8 and 8 in this case, that's more than likely a 45-degree reference angle. And yeah, not more than likely, exactly a 45-degree reference angle. So we're talking about 45 degrees away from 360. The angle theta is 315 degrees, just by looking at it. So I didn't have to use any trig equations for that. What about the radius? That one I can't just look at and spit out the answer right away. Or I might be able to, but I'm not going to try. I'm going to use the formula. Formula, square root, a squared plus b squared, or x squared plus y squared. In this case, 64 plus 64, because we're talking about the same value. Negative 8 or positive 8, when you square them, you get 64 for both. I have to add them, which is 128, square root it. 128. I think that's, well, I could have just written the 64 as 2 times 64, or the 128 is 2 times 64. 2 stays inside, 64 comes outside as an 8. 8 squared of 2. You can double check how that works, but 128 is 2 times 64. 64 square root comes outside as an 8, 2 stays inside. So we have r and theta, so then z is equal to, there's two ways you could do this. There's the lazy way, and then there's the formal way that they wrote up on top. The lazy way is not an informal way. It's just the way that they defined it. It's going to be different. So the way that I normally write it is r and then an angle theta. And there's numbers to represent those. So literally, and this is what we call phasor form. Physicists and engineers use phasor form. It's an even lazier way to write complex numbers. So how would that look like here? 8 square root of 2, and then the angle, 315 degrees. That's the phasor form. They don't want it in phasor form, they want it in trigonometric form. What's the trigonometric form? 8 square root of 2, and then they told me we could do this. CIS, cosine I sine of 315 degrees. So not too much tougher than just drawing an angle sign. CIS is super easy to write. What's the formal way that they initially introduced it? 8 square root of 2 cosine 315 plus I sine 315. That's the formal way. These are the same though, so I could box either one of those two. No big deal whatsoever. So that's letter A. And I kind of did the math a little quickly there, but there's a graphical way and a graphical understanding behind what I wrote for either of those situations. We'll look at letter B, see if we can come up with a similar answer. So for letter B, negative 15. And this is one of those situations where it's so easy, it might psych you out a little bit. But graph it first. That's usually the best way. So if I graph it, where's negative 15 on the coordinate plane? Remember, negative 15 is a real number. There's no imaginary part to it. And if it's a real number, it goes on the x-axis. And because it's negative, it's on the left side. So negative 15 this way. And that's literally the point. So it's this vector stemming from here. So I have to find out the radius or the distance and the angle. Angle's easy. If it's a negative real number, the angle is 180 degrees. Negative real numbers have a phasor angle 180 degrees. positive real numbers are 0 degrees. What about something on the y-axis? Well, if it's on the positive y-axis, that's 90 degrees. And if it's on the negative y-axis, it's 270 degrees. So those are kind of easy to remember. And when you kind of get used to thinking of these as angles and distances, complex numbers instantly become much easier to work with if you're very comfortable with the geometrical stuff. So negative numbers are literally just 180 degree angles. So that's kind of cool, thinking of numbers as physical positions on a paper, on a coordinate grid, on a rectangle. So negative numbers are literally 180 degree angles. So the only difference between different sizes of negative numbers would be how far out it is along that line. So this one's 15 units to the left of 0, or 15 units away from the origin at a 180 degree angle. So the angle is 180 degrees. The radius, or the distance, or the modulus, or the magnitude, all of those things are the same thing, 15. So you have to be careful here. No negative there. Once you say it's a negative, or once you say it's a 180 degree angle, negative sign goes away. So it's the number 15 rotated 180 degrees. So it's literally just the number 15 at 180 degrees. So then what's the phasor form? 15, 180. Or in trigonometric or polar form, 15 cosine 180 plus I sine 180. That's the trigonometric way, the way they want. So that's how we represent it, as a distance and an angle, or a vector in this case. But we're talking about the distance and the angle of the vector as opposed to the x and y components. So what we're really doing is we're transforming back and forth between an x and y representation and an r theta representation. So rectangular coordinates versus distance and angle. And that's example 3. So we'll keep on going. Okay, so number 4, I'm minded to skip. So moving back and forth, I'm going to go ahead and just continue. I'm not doing example 5. That's a Julia set application. Or is that a Julia set or a... Yeah, it's a Julia set. So it's kind of cool. Julia sets kind of look like, well, these are fractal patterns. And those are very similar to like the Mandelbrot set. So these are different types of fractal patterns that people have noticed on complex numbers. We won't go over those though. Wish we had the time for it, but we don't. So the two major takeaways for the end of the section: how to multiply and how to divide geometrically. So these look a little uglier at first, but once you get comfortable of thinking of special complex numbers as angles and distances, division and multiplication are easier this way. So we're going to do it both ways: the rectangular way to multiply and then the polar way to multiply. And then you can be the judge as to what you like better. But more than likely, you're going to end up liking the polar way. So we'll talk about these two numbers. Find the product of those two. So they gave instructions on how to multiply two complex numbers. To multiply two complex numbers, all you need to know: a plus bi times c plus di. These are two complex numbers. We've already learned how to do this. You distribute, you FOIL, and you combine like terms. AC plus ADI plus BCI plus BDI squared. I times I is I squared. So that's what this is equal to. I squared is -1, so you end up getting AD minus, or AC minus BD. That's this one and this one added together. And then you'll just factor out the I. So that's AD plus BC times I. And there's the answer. That's how you multiply two complex numbers. So that's the way that we used to do this. That's what they're saying up here. And that's a little bit, and actually no, that's not what they're saying. What they're doing here, yeah, so I'm going to demonstrate how they get this with this particular example. So there's a way to prove that, and it's kind of an ugly proof, and I'm not going to show the proof here. But what's required in the proof is you're going to distribute these terms, and when you distribute them, you're going to get two sum formulas. You remember the sum formulas for cosine theta plus something else? The cosine, 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 sine, sine, sine one. And this one is sine, cosine, cosine, sine, if you remember those. So it requires that, but I'm not going to take the time for the proof of those. So the proof's not too important. It's just another application of the trigonometric identities, which we've already mastered. So we'll see that later. I'm not going to go through the proof, but I'm going to demonstrate why that's true. So we'll illustrate using this example. So let's talk about this one, and I'm going to call this one Z1. This one I'm going to call Z2. And what we're really looking for is Z1 times Z2. So what is this product? So what happens when I multiply both of those? So first off, what is Z1? 4 cosine 120 plus I sine 120. So we're going to have to look at our unit circle again. Cosine of 120 and sine of 120. Cosine of 120, that's going to have a reference angle of 60 degrees. And that one's 1/2, negative. So 4 times negative 1/2 plus square root of 3 over 2 times I. Z2, 30-degree angle. So 30-degree angle, 5 on the outside, inside, square root of 3 over 2, plus, you notice how I'm writing the I first here? The I feels more natural if I write it first, kind of. Depends on how I'm feeling. These things don't want to erase. Plus I square root of 3 over 2. You can write the I first, no big deal. Because they wrote the I first here, so I might as well just write it first. 1 over 2. So because cosine of 30 is square root of 3 over 2, sine of 30 is 1/2. So hopefully that's easy to verify. So I got to multiply both of those. So that's 4 negative 1/2 plus I square root of 3 over 2 times 5, because we're multiplying everything, square root of 3 over 2 plus I times 1/2. And I got to multiply. So I can move things together. And I'm going to move the 4 and the 5 together. Those make a 20. And then I'm going to multiply these two, which is going to suck. Negative 1/2 plus I square root of 3 over 2 square root of 3 over 2 plus I 1 over 2. And then we distribute like we did over here. So I have to distribute those. So then we have negative 1/2 times square root of 3 over 2. 20's on the outside, along for the right. Inside parentheses, negative square root of 3 over 4. Remember, you multiply across. Numerator with numerator, denominator with denominator. The 2 times 2 on the bottom becomes a 4. Negative 1 times square root of 3 is negative square root of 3. And then plus these two. Negative 1/2 times I times 1/2 minus I times 1/4. Double check how I got that. So I'm not going to explain too much. I times square root of 3 over 2 times square root of 3 over 2. So that's where I got to be careful. Plus I 3 over 4. Hopefully you see that. Square root of 3 times square root of 3 is 3. 2 times 2, 4. And then there's just an I along for the right. Keep on going. That's where it gets a little tough. So that's plus negative 1. I times I is negative 1. Square root of 3 over 4. Now I want to make sure I'm doing this slowly and making sure that I'm not rushing this and making some mistakes. So it looks like I'm fine. So then we got to simplify by combining like terms. 20 still out here. And what like terms can I combine? These two right here for sure, because those are real numbers. So I see negative square root of 3 over 4 and another negative square root of 3 over 4. Negative square root of 3 over 2. It's going to be 2 square root of 3 over 4. 2 over 4 reduces to 1/2. So it's negative square root of 3 over 2. These two combine. So negative I 1 over 4 plus I 3 over 4. Negative I times 1/2. Negative 1/4 plus 3/4 is 2/4. 2/4 is 1/2. And that's the answer in rectangular form. Actually, no, that's in polar form. Because that's, let's see. No, that's not in rectangular form, sorry. Rectangular form is going to require me to distribute the 20. One more step. So that's negative 10 square root of 3 minus I times 10. So negative 10I. And that's the answer in rectangular form. Look at all the work there. That's quite a bit of work. Let me erase this. That's how you multiply using rectangular coordinates. We've already known how to do that. That's something that we saw in 1.3. So multiplying complex numbers requires distribution and combining like terms. So why did I say earlier that in polar form it's easy? We haven't really seen it in polar form. So what we did was translated that polar form into rectangular and used what we already knew. So let me show you what that looks like in polar form. So let me make that even easier in phasor form. So we're multiplying 4. So the phasor 4, 120 is going to get multiplied with the phasor 5, 30. So this right here is the rectangular way to do it. And this over here is the polar way. Let's continue. You just distribute 4 and 5, 20. So the 4 and the 5, so the magnitudes get multiplied and the arguments get added. Literally 120 plus 30 is 150. 20, 150. And we're done if we leave it in polar form. But they don't want it in polar form. They want it in rectangular form. So then 20 CIS of 150. So then you do 20. What's CIS of 150? Well, first C, cosine of 150. What's cosine of 150? So you look at the unit circle. Negative square root of 3 over 2. Plus sine of 150 times I. So I times sine of 150. What's sine of 150? 1/2. So verify that on your unit circle. So then if I distribute, negative 10 square root of 3 plus 10i. Is it the same thing? I got something slightly wrong. So there's one little mistake, and I think my mistake, and you probably already caught it while I was working, and what was it? The 2 in the middle. The negative 1/4, positive 3/4, wasn't that positive 1/2? So that should be a plus here. So I apologize deeply if you saw that mistake and either got confused with me writing a negative and not a positive. But yeah, that should have been a positive. So sorry about that. I'll probably edit in there a correction as I'm speaking for that part there. So yeah, they should match. So notice how this one's longer. This version sucks. And there's more room for mistakes. So that kind of proves my point. So that wasn't on purpose. I just really suck in math. So I was supposed to write a positive sign instead of a negative sign. So that was not on purpose. That was by accident. So there's more steps. More steps means more chances, the higher chances of making mistakes. This one, a lot less steps, very easy. And I caught a mistake using the easier method because it's a lot easier and less room for error, I guess. So I like this one better. You probably like this one better because it's a lot less work. So what's the explanation? So what did I do? So let me slow that back down because I kind of went that fast. I kind of went kind of fast. So you write them as phasors, a magnitude and an angle. So the magnitude 4, angle 120. They told us that. Magnitude 4, angle's 120. You do the same thing for the other one. Magnitude was 5, angle's 30. So when you multiply two phasors, you multiply magnitudes. So multiply magnitudes. That kind of looks weird. So you multiply magnitudes. You add angles. Those are instructions. So you multiply magnitudes, you add angles. That's when you're multiplying two phasors. And then if they want it in polar form, you change it to polar form. And that's what I did from, so literally the math was done here. I had to continue going because they didn't want it in phasor form. They wanted it in trigonometric form. So all of this right here is the math to change it to trigonometric form. But the actual multiplication step was done in one line. So it's pretty simple. So that's what I skimmed over here. So this is what they're saying here. This is the product theorem. In compact form, if you want to add two phasors, some magnitude times some angle plus another magnitude times some angle, you literally multiply the two magnitudes and you add the two angles. That's it. You multiply the magnitudes and you add the angles. And I kind of illustrated how that works by changing it to rectangular and proving that it works basically for this one particular example. So we can actually complete a proof for all r's and thetas. I'm not going to do that though. I don't feel like it. So there's that. So what I would do is I would do this work. This is the way I would do this. That's why I'm saying sometimes it's easier to work with complex numbers. That whole spiel that I went with at the beginning of the section, how this is a very much more convenient way to do math. It's easier to work with complex numbers because it's angles and distances. We could think of them as vectors, and having to think of numbers as vectors makes it much easier to do much more complicated mathematics. This is one of the illustrations as to why thinking of them as vectors is much easier. So we'll move on. Division. Very, very similar. There's another very easy application for division. So if I want to divide two numbers, so look at it this way. So they're writing it in complex trigonometric form up here. So that's the compact CIS function. So r times CIS theta, and then r times CIS theta for two different z's. So that's the same thing as z1 over z2. You literally divide the magnitudes and then you subtract the angles. So you divide magnitudes and then you subtract angles. So those are the instructions for dividing. So let's try that with number 7. I think number 7 is the last one, and we're done with this section pretty much. So let's put that into practice for number 7. So here they're already writing them in phasor form, technically. Write the result in rectangular form, so those extra little instructions, we can deal with it. So how do I divide those two? This right here is literally 3, because 27 over 9 is 3. Cosine I sine of, crap, I gotta subtract those. 45 minus negative 180 is 45 plus 180. What's 45 plus 180? 225? See, if they wanted this in polar or trigonometric or phasor form, this is done. It's literally it. You divide and you subtract, and we're done. But they want it in rectangular form because they're jerks. So we'll go ahead and entertain them. That's 3 cosine 225 plus I times sine 225. Unit circle, hopefully you have that handy. 3, and then what's cosine 225? These are square root of 2 over 2 and negative square root of 2 over 2, depending on what quadrant we're in. This one's quadrant 3, so both of them are negative square root of 2 over 2. And hopefully we're okay with that. That's just unit circle. Now what do? We distribute the 3. Polar form should not have, rectangular form shouldn't have things like this where it's factored. It should be just a real part plus an imaginary number. So negative 3 square root of 2 divided by 2 plus I 3 square root of 2 over 2. And that's it. So that's written in rectangular form. And that's going to go ahead and conclude this particular section. So we'll stop here for 8.5. Continue with 8.6 in the next video.